So again, there are certain issues, certain points which you have to remember with regard to selection of the mobile phase. So initially you have to look for certain solvent. For example, if you are using water, then you know that water is a very polar solvent, and most of the buffers are made in water. So water is also a base for the different buffers. Water is also a universal solvent. Similarly, if you are using acetonitrile, then of course there are very good thing for acetonitrile. It has very low viscosity. Its UV cut is very less. For example, it is 190 nanometer, and it has very good elution with regard to the reverse phase HPLC. Methanol, which is also a good solvent, but its cutoff is little high, that is 205 nanometer. It forms strong hydrogen bonding because of the presence of this OH group, because of the presence of this electronegative atom. It has higher viscosity. Similarly, if you are working with isopropanol, that is IPA, then it has higher viscosity. Okay, and it is actually, sometimes it is used as a modifier, as a mobile phase modifier. Now, it's a comparative table of different solvents. You can see the cutoff here. For water is 190, acetonitrile close to 190. These are a little higher end. Now viscosity, it is 1. You can see the viscosity of acetonitrile, it is very less. The viscosity of isopropanol is twice as high as water. So it is itself a solvent, itself a mobile phase, but it is also a buffer base. Similarly, acetonitrile is used in UHPLC because of its very low viscosity. Again, methanol is good, it's cheaper, it's economical, and it forms hydrogen bonding. Here high viscosity is there, and it is only used for special cases. Now buffer selection, and the buffer selection with regard to the pH. Now we have to choose the buffer with regard to its the pK value. So for example, the most commonly used buffer are the phosphate buffer, which is non-volatile, but at the same time we have some volatile buffers also there. For example, acetate and formate, and we have ammonium formate acetate buffer that we generally used while working with the liquid chromatography mass spectrometry. So generally we use the concentration range of these buffer is from 5 to 50 millimolar. So the moment you increase their strength, the precipitation may also occur with organic solvent. So you have to look all these factors, and also we have to we have to also look for the common ion effect also while working with buffer solution. So if you are using phosphate buffer, then it is, you cannot use it for the mass spectrometry, because in certain cases it may lead to precipitation, and if precipitation occurs, then of course clogging may occur. So you have to avoid the phosphate buffer. Similarly, this is the well-known Henderson-Hasselbalch equation, which gives you an idea about the pH of the solution. And here, as I have said, that you have to look for the common ion effect. Okay, so you have to choose the buffer very intelligently. Now pH actually affects separation, and it changes. For example, if you have a low pH, the below Ka, then protonation is there, and then it leads to polarity, and polarity leads to lesser retention time. And we have seen that, and these cases occur in case of reverse phase HPLC. So you have to check for the pH, and also you have to check for the effect of pH on the stationary phase. So if pH is too high, you have to take the stationary phase very cautiously. You have to choose it very cautiously. Now, if you have a high pH above pKa, then it is deprotonated, again more polar and less retention time. So practically you have to choose pH with regard to the analyte, and you have to also look for the ionization, because it changes the retention time and also it changes the peak shape. So at extreme pH, that is greater than 9, the silica also starts bleeding, that it also destabilizes, and it starts coming with the analyte. So you have to check for the pH also. Now organic modifiers, that in certain cases you have to add certain solvents to get a good resolution, and we have seen that in the previous slide where we have used PDA as the modifier. So, for example, acetonitrile. Acetonitrile, as we have seen, it has very low viscosity, and that because of the low viscosity, you always experience a very low back pressure, and it gives sharper peaks. And it, with regard to selectivity, it has very different selectivity with regard to methanol. So, at the same time, if you change the solvent, then you will get different dilution strengths or different dilution pattern. Similarly, methanol, it can change selectivity because of the presence of the oxygen, and it leads to hydrogen bonding. And if you are using methanol as a solvent or as a modifier, then because of the presence of the electronegative oxygen atom, it can interact with the polar analytes, and because of the interaction, it can change the retention times. Similarly, trifluoroacetic acid improves the peak shape, and it is generally used for the separation of peptides, but at the same time it suppresses the mass spectro signal. So you have to check that whether your modifier is good for your detector or not. So this acetonitrile is a strong eluent, has low viscosity. It is very good while working with the ultra high performance liquid chromatography as well as the mass spectrometry. Methanol, it gives rise to hydrogen bonding. Now it is very best for polar interaction as well as for the chiral separation. Now if you mix the two solvents, then you actually tune the selectivity for the separation of different components, and it is very good for the complex mixture where you have a set of polar analytes. Now let us compare isocratic mobile phases and the gradient mobile phases. As we know that isocratic mobile phases are those where we have a constant mobile composition, where the polarity remains constant throughout the separation process, while in gradient you actually keeps on changing the mobile phase polarity so that you can have better dilution, so that you can have longer retention times. And this is actually the newest one, because earlier isocratic was the traditional mobile phase taken traditionally. So isocratic, as we have said, that it is here the polarity remains constant throughout the composition. It is very good for the separation of simple compounds, but the limitation is that if for example if you have this type of separation, okay, if you have this type of chromogram, then you can see a long time. But at the moment, if you change the polarity, this is for example, this is for isocratic. The moment you change the polarity, you can have this type of one. Okay, this is called gradient one. Here you have changed the polarity. So gradient, here the composition changes. So advantages is this compressed peaks, better through output for complex mixture, and it is suitable for trace analysis. But the limitation is that for more complex to validate, you have a dual volume. Sometimes dual volume also comes into play. That dual volume is that volume which is the volume of the mobile phase inside the column, that is from the point of insertion of mobile phase up to the point where it actually analyzes. That volume is called as a dual volume, and because of the dual volume sometimes you get unaccounted peaks. So gradient steepness is there, and you have to always look if in case of gradient elution or gradient mobile phase, whether you are missing any peaks or not. So you always have to be very cautious while using the gradient mobile phases. So initially, what are the parameters? Let us quickly look into it. So it initially the important parameters are, it influences the focusing of solute at the column head. So dual volume is there. Again, it is the dead volume, and it actually alters the gradient reaching from the column head to the transferring. So it actually changes. Similarly, how you can avoid them? You have to run column scouting gradients. Column scouting is actually the process where you choose different columns and different mobile phases, tries different combinations of columns and different combinations of the mobile phase to select the best column with regard to best mobile phase. So by doing scouting gradients, you can actually take care of the dwell volume. So two instruments with identical methods can behave differently because of the difference in the dwell volume. Okay, so you have to keep an eye. Now temperature control and the effect in terms of the Van 't Hoff relation. So we know that the moment you increase the temperature, viscosity increases, the diffusion leads to mass transfer and the partitioning occurs. So this Van 't Hoff equation, this one which we have already, which is very well known equation. So if you draw a curve, then you will find a linear log n curve versus 1 upon t, and the slope gives you the delta H value. So you have to take that temperature where you can get a good Gaussian narrow peak with a short run time. Okay, and if you are taking the same temperature, then you will have good reproducibility. Okay, so temperature programming is very important, and in GC we have seen that by doing temperature programming you have shortened the run times. So the hidden fact is that you have to do temperature programming very judiciously, and you have to also look that in terms of doing temperature programming, you have to cool down your equipment to the room temperature so that you cannot miss the peaks which are coming at close to room temperature. So it is always advisable to start your GC at a temperature at least 20 degrees below the boiling point of the least volatile or least component of your mixture. So again, efficiency versus speed, we have already discussed it at length while we were discussing the elution chromatography, as well as while we were discussing about the gas chromatography. So the equation, the well known equation, is H is equal to H is height equivalent to theoretical plate, A plus B upon U plus Cu. So we always take optimal velocity, and this optimal velocity is toward the higher side. So if you have faster flows, of course you have lesser analysis time, but at the same time this will increase the Cu turn, and this lead to band broadening. So the rule of thumb here is that when changing the particle size of column internal diameter, adjust flow to keep the same linear velocity throughout. And for coarse shell particles, the optimum velocity is always higher as compared to the fully porous particles. Okay, so you have to keep this hidden fact in mind. Okay, now the detector compatibility and the mobile phase constraints. For example, when you were using the U visible detector, or where you are using the PD detector, so avoid solvents or buffers with a strong UV you can say cutoff, so that it cannot interfere with the one which is because of the analyte. So you have to judicially choose your solvent so that it cannot come close to the lambda value of your analyte. Similarly, while using the IMS detector, avoid those buffers which can clog or which can have an ion pair agents. Okay, so always use the format and the acetate buffers. Similarly, if you are using the RI type of detector, that is the refractive index detector, then by using the RI detector, you cannot have a gradient elution system, because this will change the baseline. This will create a noise in the baseline, and you will get unstable or not very well defined analytic peaks. Okay, so you have to look for the detector. Similarly, if you are using the EC detector, then you need actually the conductive buffers, and you have to remove the oxygen you have to do purging. Okay, you have to do purging. Otherwise, the oxygen may have an effect, or it will change the conductivity little bit. Now, these are the summary with regard to the mobile phase. For example, if you are using the UV detector or PDA detector, then of course there is no requirement of volatile buffer, so it is gradient friendly, you can use it. Okay, similarly, if you are using the mass, then okay, volatile buffer is required. Yes, it is required. It is gradient friendly also, you can change the polarity, and it prefers the volatile salts. Now, if you are using RI detector, then again there is no need to use a volatile buffer. It is not gradient friendly also. Okay, so you can use the isocratic mobile phase, that is the mobile phase which remains constant throughout. Similarly, for electrochemical detector, there is no need for using a volatile buffer. Okay, gradient friendly, yes, it is gradient friendly, but you have to monitor the change in the polarity, because at some times electrode fouling occurs. Now, this is actually a step-by-step workflow. So, initially what you have to do, you have to look for the analyte which is to be separated. Now, you have to look that how much resolution you require, what is the limit of detection, how much runtime you can afford. Okay, similarly, you have to do scouting, you have to look for the best column with regard to best mobile phase. So you can choose different mobile phase. It is actually choosing the best combination of the column with the mobile phase with regard to compatibility of each other. So you can have the C18 stationary phase, you can have a phenyl, so that you can have a partially polar stationary phase, because here it is non-polar, here it is partially polar, and here it is fully polar, highly polar, HILIC. So you have to look for which type of stationary phase you want to use, and which type of or how much length of column is required. Similarly, you have to choose that which type of mobile phase it actually require, that what is your viscosity requirement, and if you are using buffer, then whether you want to use the volatile buffer or you can be good for non-volatile one. Similarly, you have to optimize the gradient conditions also, and you have to fine tune your pH value and also the buffer strength. Similarly, you have to adjust the temperature and also the flow of the mobile phase, so that you can get the optimum velocity of the mobile phase and the best reproducible temperature, so that you can every time you will get the same number of analytes contained in your mixture. Similarly, sustainability and robustness test, that is, you have to look for the value of the efficiency, you have to avoid tailing, and also you have to look for that you have to start from taking the small or short columns, because if you are using the short columns, you always need a small amount of solvent. Once you get the optimization is done, you can increase the column length, and of course, if you are using a long column, then you need a large amount of sample. So before you have to do optimization, and then you have to go for throughput screening. Now, validation and robust check. So what are the key parameters? So initially, you have to have specificity, you have to have linearity, how much linearly your detector is generating the response. It must be as large as possible. Similarly, how accurate your results are and how much precise they are. You have to check for LOD, limit of detection, and also the limit of quantification, that how much you can actually read. What is the least amount which you can read from your equipment, from your instrument. Similarly, the range, the robustness. Now, the robustness testing can be done by changing or by varying the flow of your mobile phase, by altering the pH, by changing the temperature. So you can check that what are the limits of your temperature, what are the limits of your flow, and on that basis actually you can have the best separation. Okay. Similarly, the acceptance. So you have to check that how much resolution is needed, and it is always less than 1.5 in any case, and in pharmaceutical industries it is one of the mandatory condition. So robustness failure often reveal that there are certain issues which are still unresolved. So you have to check for buffers, you have to check for your solvents, you have to check for the gradient elution or the isocratic elution. So you have to check each and every point so that you can have the best separation. Now in case of pharmaceuticals, for example, you generally use the reverse phase HPLC, where you take the C18, which is actually a non-polar stationary phase, and the column length is generally 100 millimeter, whereas the diameter is 4.6 millimeter, and the particle size is to be somewhere between 3 to 5 micrometer. But if you are using for UHPLC, then you have to take a smaller particle. Here mobile phase is generally very polar. Most of the time we use water or some volatile buffers. Again, the base is water. Sometimes we also use acetonitrile in case of, and we also use methanol as organic modifier, so that we can have better resolution, better separation. Here we use the UV detector or PDA detector. Sometimes we also use the mass spectrometry to identify impurity, or in case the presence of some unknown compound. So quality control assays for actually uses the isocratic elution or shallow gradient elution, so that you can have good efficiency and you can have less tailing effect. So force degradation studies use multiple columns and pH range to reveal impurity of chemotypes. You have to always look that your sample, your drug should be as pure as possible and does not contain any ghost peak or any unintended peak. So with regard to food and environmental analysis, for example, here you use the C18. For example, here you use FLD detector, fluorescence detector. Again, if there is no fluorophore, then sometimes you use tagged fluorophore. It is very good. As we have discussed, this HILIC is very good for the detection of certain anions, for the detection of sugars. Here you use very polar stationary phase, and generally you use the RIT type of detector or CED detector, which are only good for doing the isocratic type of mobile phases. Similarly, for pesticide you use generally the ion exchange chromatography, and here you actually couple your detector with a mass for the trace detection of various components of a pesticides. So HPLC allows targeted quantification and multi-residual screening if you couple it with MS, that is mass spectrometer. But again, there are certain limitations. For example, you have to carry out the regular cleaning of your column of your detectors, so that no unwanted or previously held samples are there. So again, silylation for GC, you have to check for some groups that may lead to clogging. Okay. Now application with regard to biomolecules, how you are going to separate biomolecules, generally peptides and the proteins, by using HPLC. So again, if you are going to separate peptides, then what are the more stationary phase and what type of column you need? Then you need again this reverse phase HPLC you can do, and here again you need the non-polar stationary phase with a large pore size, because now these peptides and proteins, they are having very high molecular weight, and we have seen that more than 1000 Da. So here you need, because of the large size, you need solvents which have lesser viscosity. Similarly, you use TFA. Okay, TFA is trifluoroacetic acid or formic acid combination, so that you can have a better shape. And again, this formic acid is compatible with your mass detector. Similarly, for proteins, sometimes you use the size exclusion chromatography, and here you have to use gentle mobile phases. Detectors, you can use UV visible detectors which have a cutoff of 214 nanometer, and again if you couple it with mass, then it can also be used for the identification of some unknown samples. Similarly, ion pair agents are there. You can always include ion pair agents, but you have to be very cautious with regard to the detector. Now, the applications with regard to the polymers, here you can use the size exclusion chromatography, and it separates on the basis of the size. That is, here this hydrodynamic radius comes into play, because here the size is important. If you are using appropriate size, then of course a separation will be good. Otherwise, if size is too big, then it is not going to hold the analyte, and retention time will be less. So you have to check for the size, you have to look for the column, so that your pore size must match with the matrix of the stationary phase. Typically, we use THF for many polymers, and sometimes we also use aqueous mobile phases. So here we use more than one detector, that is called as the detector combos. For example, we use RI with MALS, that is RI with MALS, multi-angle light scattering detector. This is very good detector for asserting the absolute molar mass. This is very good, MALS. So the size exclusion chromatography requires the careful choosing of the stationary phase with regard to the appropriate porosity. Now, column, there are certain issues which comes, and how we can resolve those issues we have summarized in this slide. For example, if the pressure is rising slowly, if the back pressure is building up, then what will be the key points which we have to look to resolve these rising pressure? We have to back flush it. Okay, if for example up to now, for example, a column mobile phase is passing from this to this. Now, in order to clean it, we have to back flush it. Okay, or we have to replace the guard column. For example, if it is connected with a guard column, if it is connected to guard column like this, then we have to check this guard column, because the work of guard column is to filter the impurities, is to filter the different particulate matter. So initially everything would be here, and your main column is saved. This is your main column. So similarly, we have to check for sudden pressure spikes, and this may be because of the column blockage. So we have to check for our frit, that whether our frit is clogged or not, whether our frit which is having very small pores throughout, whether these pores are open or not. Similarly, we have to check for the peak tailing, and this peak tailing arises because of the certain components of the analyte forms a partial bond with the SiOH group. Then this will cause issues, and you have to do end capping. So we have to check for the peak tailing. This will arise in terms of peak tailing. You can avoid peak tailing by doing the end capping. Similarly, split peaks. So split peaks may arise because of the solvent mismatching. So we have to change the solvent system, and sometimes we have to also look for the injection ports. Similarly, if the baseline noise is coming, then we have to check that whether there is some formation of bubbles. Okay, so in that case we have to do degas our mobile phase, so that we can rule out the presence of any oxygen, or we can, in some cases, the lamp is to be replaced. The UV lamp, which is generally the hydrogen or argon based lamp, that needs to be replaced. So always you have to do a blank wash gradient, so that you can have a good separation all the time. Now let us solve few problems. So quickly we are going to see the problem. For example, this is the data. which is obtained from HPLC. Here T naught is given to 1.5 and the solute is elucidative different time, that is here it is TR. So the formula is simple. K may be defined as, that is retention factor may be defined as TR minus T naught upon T naught. You just populate all the readings in this equation and you will get K 2.4. Similarly, another problem, here two solutes are given which have the retention time, that is TR1 and TR2 4.2 minute and 6.3 minute. You just put in the formula to calculate the selectivity, that is selectivity may be defined as, that is TR2 minus TR1 upon TR1. Now the important thing is that you have to always bear in mind that the one which is eluting last is always TR2 and this is TR1. So you substitute the values and you get alpha 1.7. That is very good value. Similarly, again resolution between two peaks, you have the same age old formula, that is resolution may be defined as twice of TR2 minus TR1 upon width of peak 1 plus width of peak 2. You just substitute all the values here in this equation and you get a value of resolution 3.03. That means it's a good resolution because this value 3.03 is greater than 1.5. That is the ideal resolution, that is the baseline resolution. Similarly, if you calculate the value of n, you have the formula here, 16 upon TR upon W square. You just put all the values, that is the value of TR here and the baseline width which is 0.3 minute here. You substitute all the values and you get 5184 theoretical plates are there. Okay, this is a good number of plates. Now required value for target RS, you need RS 2.0. For example, you can take any value of RS greater than 1.5. Here you have used a target value of 2.0 and now you actually calculate the number of theoretical plates with this target value. So the equation is here, RS is equal to under root of n upon 4 alpha minus 1 upon alpha, K upon this alpha is selectivity, K is the retention factor. You just solve it for n, you get this value. Okay, under root of n you get this value. So in order to have a resolution of 2.0, you need, now let us calculate, let us use the Van Demeter equation. For example, we have to find the optimal velocity here. Optimal velocity, the equation is here. So you solve it, you will get a 3.16 value which is arbitrary units. Now with this, you substitute here in this equation this arbitrary value and you will get the H minimum 3.52. So this is the minimum height of your theoretical plates, that is 3.52 micrometer. Now let us do another example. You transfer method from 4.6 millimeter IDF column to a 2.1 millimeter internal diameter column. So original flow rate is this. Now find a new flow rate. So new flow rate is maybe defined as by this equation. So simply just put all the values here, you get a flow rate of 0.21 ml per minute. This is the flow rate where you have transferred in the new column which has a diameter of this. Okay. So another problem, retention time. So if the flow is doubled, then retention time ideally becomes half. That is an isocratic system. So it is here the simple formula. So from 6 minutes you will get a 3 minute. Okay, in terms of isocratic system. Now gradient delay volume correction. For example, you have a dual volume, it is given 1 ml and your flow rate is actually 1 ml per minute. So you have to program your gradient. Now the formula is T delay may be defined as dual volume upon F. So you put all the values, you get the gradient will start from 1 minute, it means. Okay. Now let us do another tailing factor problem. Now the peak width at a 5% height. Here it is given, A is given as 0.15 and B is 0.25 and the tailing can be calculated by a simple relation, that is A plus B upon 2A. So if you substitute all the values, you will get 1.33 values and this is an acceptable value. Okay. Let us calculate HETP. Again, that is height equivalent to theoretical plate. For example, HETP can be defined by simple formula, length of the column, which is, you can say, filled column, upon the number of theoretical plate. Here length is 150 millimeter and number of theoretical plate are 7500. You just substitute it, you will get a value of 0.02 millimeter. So 0.02 millimeter, you convert it into micrometer, it is 20 micrometer. Okay. So another peak broadening problem, let us do it quickly. System peak broadening due to extra volume. So system volume adds 0.1 minute width. The true peak width is 0.3 minute. So observed width is 0.4 minute. So how you are going to calculate the percent? It is 0.4, that is the observed one, upon the true one. So you just divide it. So the peak width increases by 33%. Okay. Now let us do another problem. That is a good problem. Ln K2 upon K1 upon delta H upon R. We have already discussed this formula in our previous slides. So you substitute all the values and you will get a retention factor here. Okay. Retention factor, that is 28% on heating 10 degree. So this actually tells you the effect of temperature on the retention factor. Okay. Because here you have heated it from 298 to 308. So just by increasing a 10 degree centigrade, the retention factor decreases by 28%. Now another gradient volume problem. Here the gradient is increased from 10 to 90% over 10 minutes at the rate of 1 ml per minute. So total gradient volume can be 10 ml. This is very useful to compare the dwell volume, and we know that dwell volume creates certain issues. Now we have a column which is 150 millimeter long and it has 750 theoretical plates. So height equivalent to theoretical plate in this case is 20 micrometer, while in the another column, which is column B, it has a length of 100 millimeter with a number of theoretical plate 8000. And if you calculate H is equal to L upon N, we know that. So you can see that here the height of the theoretical plate, it is 12.5. So since it is small, so we can say that column B is more efficient. It will give better resolution. With this, we are end on this, and I'll be happy to interact with you, to solve your questions, to solve your queries. Till then, thank you.